Okay, so the material that we go over today is the new material for this week. Next week we'll have different new material. So this, I understand that you guys, like lecture group 2 is the only group, people in this room currently is the only group who's going to see this lecture this week live, but this is the material for this week. So lecture group 1, hopefully you're watching this on video after it comes out, okay? So you should expect to have different material next week for us to look at. So we're going to get back to on pattern just like we always have been. I have not graded exercise number 2 yet. That was the last thing to do on my to-do list that I started at 8 a.m. this morning and did not quite get through with before class today. I will look at that either later this afternoon after class. Probably not, if we're being honest. I probably won't do that, but I might. But definitely by Friday. I've got a full day of class tomorrow, but definitely by Friday. And also target the next assignment coming out on Friday as well. Okay, so a continuation on exercise number 2 is what you can expect. For exercise number 3. Okay. Right, any questions for me before we get started? It just occurred to me, do we know when our first test is scheduled? Let's look. Don't want to let that sneak up on us. I'm not sure I have scheduled it. And if I haven't, then we'll do that. I'll probably talk about that next week. Does it say anything? Let's look. Okay. The schedule. Yeah, so it looks like exam 1 is scheduled down here. So we've still got a couple of weeks to go before we look at that. So anyway, keep that on your radar. It's coming up. Be here before we know it. All right, so we had been talking. Oh, you guys need to see the screen. Okay, so we've been talking about processes, okay? And more generally, units of processing, okay, from the OS perspective. What does it mean to run a process from the perspective of the operating system? We introduced the notion of processes. We kind of talked about the relationship between processes and programs, and that's pretty multifaceted. We talked about some of the structures that go into making a process, some of the things we need to be able to keep track of with processes. So, critically, we talked about the simple finite state machine for all processes, right? Ready, running, and blocked. Okay, and we talked about also critically the transitions, the possible transitions between those states in the finite state machine and what triggers those transitions. Okay, so those are the things that are the high points from the first half of chapter 2. So today we're going to continue with the second half of chapter 2, and that's 2.4 through 2.6. Okay. All right, and the first question that kind of comes out of that is, where do processes come from? I want you to appreciate the nature of the bootstrapping problem that we have here. If I can spell. Bootstrapping. You guys know what that term means? Bootstrapping? What does it mean?
Pull yourself up by your bootstraps.
So that's the common usage, sort of the common metaphor where you start yourself, right? You pull yourself up by your bootstraps as, you know, you are a self-made person or whatever. And it's a similar idea here. The bootstrapping process is the process of getting started, okay? Starting from nothing, right? So how do we get processes started from nothing, right? And where do processes come from? What entity is in charge of starting processes, right? Because everything, every bit of computation that a computer can do, right, at least as long as the operating system is loaded, involves running a process. Okay? So there's an inherent chicken and egg problem in here, sort of a paradox almost. So we need to break this paradox. Which came first, the chicken or the egg, right? If the egg came first, who laid it? Right? If the chicken came first, where did it come from? Okay? Because they have to be hatched from eggs. And if there was no egg, where did it come from? Right? And that is all true because of this simple fact. Processes spawn processes. And there is no other origin for processes. Right? You might say, well, the operating system makes processes. But if you break down the operating system into its component parts, what is it? It's a bunch of processes. Okay? This is like, where do processes come from? Okay, so generally what we call bootstrapping, and I'm not going to, at this level, spend too much time on what happens before the operating system loads. Okay? But operating systems have to be designed so that the hardware can run a program, a very simple program, to start loading the operating system, which, as you'll recall, the processes that make up the operating system, because the operating system is just a bunch of processes. Okay, interrelated processes. This little program is often called the boot loader. Okay, and it can exist on a special known place on the disk. And the hardware can be set up so that it is hard-coded to look for the first instruction to execute when it starts up, when you first power up the machine, right, at the location where this bootloader exists, okay? And again, depending on how the architecture works, this bootloader is either going to load the first process, okay, of the operating system, or it's going to load a slightly more complicated program that then loads the first process of the operating system, okay? But starting from scratch, no power to the computer, turn the computer on, the boot up process is look in this cache on the hardware. This cache says look to this location on the disk. This location on the disk always has the bootloader, and we begin executing the bootloader, and the bootloader spawns a process, okay, the first process, if you will, okay? Now, all of this, I will mention, all of this is the pre-operating system lifetime of every computer's use, right? If you think of the computer use as power on to power off, okay? There's a brief period of time where the operating system is not loaded, okay? Because the operating system is a bunch of processes, and processes can only be loaded from running processes, okay? So how do we get from no processes to an operating system? Right? There has to be a period of time where no operating system is actually in charge of the computer. And during that time, we have to have a set, fixed series of steps, right, that represent booting the computer. Okay? You probably, I don't know. When I was your age, I sat in a computer lab much like this one in Tuscaloosa, and I knew of turning on the computer. The slang for that was to boot up the computer or boot the machine, right? Still is. Okay. What does that mean? It means start the operating system. Okay. Go through the boot loading process. Okay. It's more complicated than that, but this is an operating system class and not really want to touch the hardware too much. Okay. But this is the general outline. So once the operating system comes online, what does that look like? All right, so the first process is the root process. Okay, this could be the thing that is loaded by the bootloader, or it could be the thing that is loaded by the thing that the bootloader loads. Okay, but this is the first process that belongs to the operating system. Okay, so roughly, this is what is happening. This first part here is what is happening, is what's being loaded when you see the Windows screen come on, okay? Windows or the splash screen for Mac OS X or whatever distro Linux you're using, and you get a little wait. This is the first thing that's happening. The root process is loading, okay? The root process also during that time loads several, however many it needs, operating system processes. And again, this is a function of the design of the operating system, how it's broken up into individual processes. Okay? And the last one that it loads is the process that is the parent for all user space processes. Okay? For everything that the user does. In Linux, this process is called init. Okay. Now this gets us to the login screen. Okay, we've loaded the operating system. Now we're faced with the login screen in front of us. Okay. In real operating systems, multiple users can be logged in at the same time. Okay, that's one of the things that operating systems do, right? And so there have been versions of Windows where that was not true. And so I would argue that those are perhaps not what I would call a real operating system, right? Okay, so it does up to this point, then it has just one user. Lame. We want multiple users. So every time that a user logs in, we get a new parent process for all of that user's processes. And the list can go on. Okay, user 1, user 2, user 3. I'm only going to focus on user 1, but you can imagine that user 2, user 3, those are all also being included, right? With adding new processes for that specific user. I'm just going to drill down on one of those as an example, though. Okay. So if the user wants to open a program, that program is a child of user 1, so forth and so on. Program in. Okay. And likewise, if these programs want to spawn other programs, they totally can. program 1 underscore child 1. These naming conventions I'm making up as I go along. Program 2 underscore, sorry, 1 underscore child 2, right? And so we get a hierarchical tree of programs, processes that are spawning other processes, okay? Any questions about that? I have not been careful. I should be careful. Technically, these are all processes and not programs. I have conflated the two terms, but I expect you to know the difference. Okay, so let me get rid of these G's, and let me put in C's for processes, because these are not just sets of instructions. These are sets of instructions running on the operating system, right? So they have the set of instructions, but they also have program counter, a program counter that keeps track of what was happening next, all the resources allocated to them. They keep track of who their parent is and who their children are. They have, each one of these has its own process control block in the system, okay? And this is the parent-child hierarchy for all the processes that are currently running on the system. All right, any questions? I think there's a inherent question here. So far, we've talked about what happens when we make new processes. I said that processes can only be started by other processes, okay? How do processes end? Well, they can kill themselves. They can say, I'm done. Okay, we entered the end of the program, I'm done. But the more interesting way is when your parent kills you, right? Because that indicates that you can be killed before you're done, okay? So let's just focus on a leaf node to this hierarchical tree. What happens when process 1 kills this process? Well, easy. And we'll talk more about the details of what it means to delete a process in just a second, okay, later on in this course. But effectively for our tree, all that means is that this thing goes away. Okay? All right, so up further, and I'm going to do this. I'm going to complicate this just a little bit. Here's a process. That thing has 2 processes, and that thing has a process. Okay? And the reason I complicate this is because what happens if the user process kills this process? Okay? The user ends that process, kills it. Okay? So this guy's got to go. He's done. What question do we have to answer? What happens to all of its children? Okay?
According to the binary search tree, we go on the right, and the smallest one on that one, we make it as the root one.
Okay.
The root.
Okay.
And then the rest goes on the right.
Okay. So you're thinking about balanced binary search trees when you talk about that. So that is a related structure, but this is not a binary search tree because these don't have values, and also even if they did have values, well, they don't. But even if they did, we haven't said that everything to the left is less than everything to the right. Okay, but you're onto something here, because if this node goes away, we've got to do something with the subtree rooted at that node. Okay? What do we do with it? Well, there are 2 possible options. Option 1, recursively Run out of room there. Recursively delete. Okay? We could say, all right, I got to kill this guy. So I'm going to kill recursively everything to the left and then everything to the right, all the left children, all the right children. Or there's no such thing as a left child and a right child. As you'll notice here, like there are 3 children here. So we're going to recursively kill every children. We're going to do a breadth first search, or rather a depth first search, kill everything all the way down the tree, back up, all the way down the tree, all the way down the tree, back up, right? So we're going to recursively kill this guy. Okay, so this guy goes away. I'm just going to make a mark next to him. This guy goes away, and then this guy goes away, and then this guy goes away, and then this one does, and then this one does. And so, boom, all those are gone, okay? There's something clean and something nice about that, right? If your parent dies, you die, okay? That's clean, that's nice. That might be a rule you want to enforce on your operating system. Okay, Windows does it that way, and it's kind of weird to not do it that way, right? Because the thing that needed me to run is dead. So what is my purpose for running? Okay, and if that's the idea, if that's the what philosophy that you have when you're designing your operating system, then you'll do it this way. The opposite philosophy is, no, processes begin processes, and sometimes those processes need to exist for a different reason than the parent needed to exist, okay? And so the children don't necessarily serve the parents, they sometimes have their own purposes, okay? And so why would we want to have a parent who is done, right, still exist, right, just so the child that is not done doing something unrelated can still exist, okay? We always want to be able to delete the parent. So the second option is to reorganize the tree. And so what I do is I get rid of this thing. This guy's the guy that got deleted, okay? And I pick up his children, and I make, right? So these links, by the way, just to clarify, these links are all 2-directional, because every process knows who its children are, and every process knows who its parent is, okay? So before I delete this guy, I remember who his parent is, okay? And then I look at all his children and change their parents to the parent of the parent that just got deleted, okay? And so now this is my new hierarchy, and everything is fine. It's just like that guy never existed. And we go on as if user 1 was directly spawning these guys, the previous subtree rooted at the thing that we deleted. Okay? Hopefully it's clear, the 2 distinctions. Hopefully it's kind of clear why you might want to do one and why you might want to do the other. Okay? Incidentally, Linux does it this way. That makes sense. Why does that make sense? Because there is only fork for creating new processes. Okay? So Linux and the Unix family of operating systems always operate under the idea that just because I was spawned by a parent process doesn't mean my existence only lasts the lifetime of that parent process, or my usefulness only lasts the lifetime of that parent process. My usefulness might be very different. I might have been a forked program that loaded a system resource, okay, that's running somewhere, and other processes are relying on me to be there, client server, that kind of thing. And just because the terminal ended, or the shell ended that spawned me, doesn't mean I need to go away, okay? And so this hierarchy needs to be reorganized. All right, any questions about this before we go on? Because I do want to talk about the details of process creation. The easiest way to do that is to actually just show you the nodes, I think. because we're going to talk about the details of process creation and the details of process deletion. Nope, that's not us. This is us. All right, so process creation. Remember, there are two ways to create a process, depending on which family of operating systems you're using. Either the create function, which is kind of what's assumed with these steps, and these are steps that I have summarized out of Zybooks, your Zybook chapter, and the fork process. So the first thing that needs to happen when you create a new process is you need to allocate a new process control block. Okay? Remember, process control blocks are the data structures that keep up with everything about the current state of a running process. So if you're going to start a new process, you need a new PCB. And it is uniquely identified either by a pointer to it, okay, or an array index. So if you are keeping pointers to PCBs, then you're doing dynamic allocation, okay? And so you update your dynamically allocated pointer to this dynamically allocated data structure, which is the PCB. Or if you're using arrays to store PCBs, you add a PCB to that array, okay? Or update the values in a blank PCB to that array, right? And again, there are some design decisions involved with that, which we discussed last time. Then some of these fields get added. The CPU state, that would be some symbol for what state out of the finite state machine the PCB is in. The memory, okay? What memory is allocated to this process? Scheduling information and accounting information. And all of those are either filled using the initial values for the parameters that were sent in if you use create function, which is why create function has a dozen or so parameters associated with it. Or they get copied over from the parent if you're using fork. Okay, those values are just copies of the parent's values. So, assuming that we only have running, ready, and blocked, the process state field is set to ready. Okay, you can't start a new process having been blocked. Okay? When do you become blocked? As a process, when do you become blocked? Incidentally, what state do you have to be in right before you go to the blocked state? Say what? That's why you moved to block, because you require a resource and it's not available, so you're waiting on a resource. What state must you have transferred out of? Running. Because you can't ask for new resources unless you're running. And you start having asked for no resources. Okay? The parent field P, which is self, which means the process that is spawning the new process, right, is set to the parent of the new process. And in turn, P is inserted into the calling process's list of children as a new child. So don't let that might be even a complicated way of wording this. But when you start a new process, not only, okay, so this guy starts a new process, not only does this guy point to that guy, in other words, this guy keeps track of a new child, but this guy's address gets stored in this guy because this guy is the child and he knows who his parent is. Okay? So the pointer to this PCB is stored as a child in this PCB, and the pointer to this PCB is stored as the parent of this PCB, giving us that doubly linked list. Okay? A doubly linked two-way connection. Okay? All the remaining fields are set to null. because P has no children, no open files, and no other resources when it gets created. And then P is inserted into the ready list. Okay? Its state is kept internally as ready, but the operating system doesn't know that until it's added to the ready list. Okay? Because there's a ready list and there's waiting list. And the ready list is associated with is a series of pointers or the PCBs themselves, some kind of data structure of PCBs that's associated with all the things that are in the ready state. And the waiting list is associated with all the things that are blocked on some resource. Okay? And the operating system won't know that you are ready to be put onto the processor, into the running state, until you get added to the ready list. Then the scheduler function is called. Okay? We started a new process. What must be said about the process that just started the new process? What state must it be in? It did something. It must have been running then. If it did something, it must have been running. Okay? So what will become the parent process can only spawn the child if it's in the running state. That's a set of operations. Okay? So now that we have the parent child, it's still running, and the parent child. Now that we have the parent process, it's still running, and we have the child process, we just put it over here in the ready list. Okay? Do we want to leave the parent running, or do we want to run the child? I don't know. That depends on what the child is doing and what the relationship to what the child is doing is to what the parent was doing. Could be that the parent needs the child to run to have some resource available to make some calculation, okay, or do something that the parent can't keep running unless the child does. Or it could be that the parent spawned a program that can take its time, and the parent needs to keep running, okay, depending on what the child does. So in order to encapsulate that relationship, we take a look at their priorities, the priorities of those two processes, the parent and the child. And we call the scheduler. We have a whole operating system component called the scheduler. And its job is to make sure that the throughput on the processor is maximized. Okay? And there's no guarantee that it will pick the child if the parent does have a lower priority. But it will pick the child before it re-uploads the parent. It will replace the parent, nevertheless. If the parent needs to stay running, according to the rules of the system, then the scheduler may not change anything. Just leave the parent running. Okay, let it keep going. And then go through the process. Either at some point it'll be interrupted because it's been determined that it was on the processor for too long, okay? And it'll be moved to ready, or it'll be blocked on some resource, it'll be moved to waiting, and some other process, maybe the child process, will be selected to go on to running. Okay? Does that make sense? Questions? Okay? What happens if you destroy a process? So you have to take the following steps. You need to deallocate the PCB data structure. If it was dynamically allocated, you have the overhead of releasing that memory. Okay? If it wasn't, you can just forget that you ever used that memory and give it to somebody else when somebody else asks. Okay? This is, of course, one of the pieces of overhead that you have to deal with if you're using an array of PCBs rather than a linked list of PCBs, because you're going to have a hole in your array now. And are you okay with that hole being there, right? And having a fragmented array, a fragmented place in memory, and having to keep track or at least check linearly again and again where all those open spaces are so you can make new ones? Or are you going to move the unused one to the end and maybe swap another one to the front? If you do that, you have to keep track of the index of the old one, the one that's running. So again, design decisions. Okay? Design decisions are involved with this. You got to remove references to the deleted process control block from the operating system. And optionally, you may have to recursively call destroy on all of the process's children. Talked about this before. Are you an operating system that allows children processes to continue to exist even if their parent or their descendant is ended, is destroyed? If you are not allowing them to exist, you need to recursively call destroy on all those children. Okay? So it's really basically roughly a 4-step process. After calling destroy on all child processes, if that's what you're doing, remove P. So after recursively calling this series of steps on all child processes, and again, this is the optional part. Okay? And also what's missing here is if you don't do that, then remember you've got to have an extra step in there which reconnects the immediate children of the destroyed thing to the immediate parent of the destroyed thing. Okay? That's not represented here. So remove the process from either the ready list or from the list of a resource, the waiting list of a resource. Okay? All right, so let's talk about waiting lists for just a second. Up until now, I've used the simplification. Okay? Up until now, I've used the simplification that you've got running, you've got ready. The scheduler can swap these out. You've got blocked, and you can go from blocked to ready. And so far I've said, okay, there's got to be a list called the ready list over here, and there's got to be a list called the waiting list over here. Okay? Generally, this is true. This might not be true. This is an oversimplification. That's an abstraction. Okay? Because in fact, there may not be a unified waiting list. There may be a bunch of different waiting lists, okay, that are all sort of combined together, where each of these individual waiting lists is associated with a specific resource, resource 1, resource 2, resource 3, okay? And we'll see that in just a minute because we're gonna broach the subject of how to deal with resources, how the operating system deals with resources. And just like when you're dealing with processes, you create a process control block. When you're dealing with resources, you can generally get away with creating a resource control block. And the resource control block for some resource keeps track of all of the processes that are currently waiting on that resource. Right? Again, here's a design decision. Do you keep a separate waiting list, which is really just a combination of those 3 things? Or when you want to know what's waiting, do you even need a list, right? Because you've already got that list distributed out across the resources, right? At no point does the operating system say, I need to move something from blocked to ready, okay? That's not the operating system. The operating system doesn't trigger that. When resources become available, right, then things can move from blocked to ready. Okay, so we don't necessarily need a unified list, because that unified list is just the union of all of these lists. Okay? All right. Again, I'll talk more about that in just a second. So remove it from either the ready list if it was ready, or from any waiting list of a resource if it was blocked. I would say it doesn't make sense that it would be on multiple waiting lists, because as soon as you're blocked on one resource, you go to the blocked state and you stop running. As soon as you're unblocked on that resource, you go to the ready state. So you can only ever be blocked on one resource at a time. Okay? Does that make sense? All right. So remove P from the list of children of the calling process. Release all memory and other resources. Close all open files and deallocate the PCB. And then call the scheduler to select the next process to run. Now, if we think about this as a program, as a series of instructions, we have to be careful here, because this might be the destroy function, where P is a pointer to a particular PCB. Okay, this is the destroy function, and if we recursively call this, so this is like step 1, step 2, step 3, based on this. So remove from the running list, delete from the list of children, remove memory, remove from running list / any waiting list I'm on, delete me from my parents' list of children, and close all open resources that I have. Okay? Does step 4 go right here? Okay? Does step 4 go right there? And why would it matter? What is step 4? Step 4 is call the scheduler. Okay? Call the scheduler. Remember, processes create processes. Processes can destroy processes. Okay? So it's possible, it's definite, that a running process called destroy for this process. The running process might be the process that called destroy on itself, or one of its descendants may have called parent, may have called destroy for the child, okay? But a running process called destroy, just like a running process called create. And so when we destroy something, okay, we call the scheduler. Just like when we created something, we call the scheduler, because the state of processes has changed, and we need the scheduler to reevaluate for us what process currently needs to be running. Okay, does that make sense? So we call a scheduler, but does it go here as part of this destroy function? It seems like it would. That's step 4. Call the scheduler. Okay? Except what? There's this little tricky word right here. Okay? Recursively call that. And recursively call destroy on the entire subtree. Do we want the scheduler to be called every time we destroy a member of that subtree? Nope. No, we don't. We want, if we're going to destroy that whole subtree as an atomic unit, we want the whole thing destroyed, right, including the parent that we're destroying, before we call the scheduler. Otherwise, things are going to get screwed up. Okay? So if we are going to recursively call this guy, then there needs to be like some kind of wrapper function. Okay? Destroy rec and destroy. Okay? And so we could recurse at some point, remove RC is recursively remove from list. Okay? And that makes it so this thing only gets called one time. Okay? Does that make sense? Any questions? Yep. All right. All right, so let's talk about resources. What resources are available to us? Talked about this before, kind of early on, talked about this. But there are hardware resources, there are software resources. It could be the keyboard, a pointing device, a mouse, or a CAD or whatever, right? It could be printers, disk drives, cameras, speakers, anything you can touch or add to the machine is a resource. Any device, any physical device that has to have drivers is a resource. But there are also software resources, input-output buffers, shared memory, virtual memory, communication lines between processes, okay? Locks on database tables, locks on memory, mutexes, semaphores. Talk about those again. We'll talk about those as the semester goes on. Timers, okay, etc. Anything to do with software. Those are all resources. Most resources can be represented uniformly in a data structure. In fact, I can't think of an example of one that isn't representable, but I can't say they all are. Okay, so we have the resource control block, the RCB. The resource control block is a lot simpler than the process control block because a resource control block isn't really actively changing. It isn't actively doing anything. We just need to keep track of a couple of things, really 3 things. The first one almost doesn't count. Here's the resource description. This is just for record keeping, the description of the resource, okay? And that is really only going to come in handy if something goes wrong, okay? Because then the operating system can say, failed while trying to access blah, this resource. And then we have its description there, okay? So resource description, availability, okay? And the associated wait list. Okay. So this is probably a string. This is a little complicated, and we'll talk about that in just a second. This is probably a list of pointers, although also, as before, it could be an array of PCBs, right? So a list of pointers to PCBs or an array of PCBs, okay? You get on this list if you request access to this resource and its availability is unavailable, okay? If it's not available, if it's being used. All right, let's drill down into this just a little bit. I'm going to come over here and drill down over here. Okay. There are 2 types of resources. Well, I mean that's a general statement, but there are 2 types of resources that we're interested in at this level. Okay. There are those which are we'll call them atomic. That's not the word the book uses, but atomic resources. Okay, they're a whole. Okay, you either they are, or you might call them binary, because you either have it or you don't. In other words, either somebody has access to this or they don't. Okay, memory addresses would be a good example of this. Okay, either someone has access to a memory address or they don't. And if they do, nobody else can have access to it. Okay? How about discrete? No, that's not what I mean. Discrete would be the other thing. I need a good word for this. Let's call it multi-part. Okay? Multi-part. Which means that multiple processes can be served at once. Okay? So atomic is easy. It's either available or it's not. That's just a bit. Okay? You just need to keep track of a bit. Here, if it's multi-part, you need to know how many there are, how many are available, and how many are currently owned. Okay? And if the amount owned is equal to the amount available, that means you got to wait. So if you're asking for this and there are none available, then you go to the waiting list. Okay? It's the simplest design for the waiting list is first come, first serve. Yeah. You might want to do something smarter than that if you're an operating system designer so that you don't have your high priority things waiting on resources. So you might make a priority queue here. Either a priority queue or just a queue would be the data structure that you would use here. Okay? What's an example of this multi-part resource? A print buffer, for instance. Okay, print buffer. Have you ever been working on a Word document and decided that you wanted to print it? Okay, and maybe you were printing a bunch of different documents at the same time, so you were like, print that, print that, print that, print that, print that. Finally, print the Word document. Okay. This is an oversimplification because Word is itself many processes, but here, you'll get the idea. And then you went back and you worked on Word some more. Okay. And the print had not come out of the machine yet. Okay, does that make sense? How can you print more than one thing to the printer? The print driver offers that resource as a multi-part resource. Okay. How can multiple people print to a networked printer at the same time? It's a multi-part resource, right? Does it has it maximized out the number of people that can be printing at it to one time? If it has, then you got to wait. If it hasn't, then you can just be off. That job is offloaded to the printer, right? And you can go on using your process, okay, however you want. That process can keep running. It's still ready, and eventually you go over there and you pick up your print job. Okay? But if that print never gets buffered, then a modal window comes up, okay, and says, you can't work on this because we're still trying to get the printer to talk to us. Okay? And so you're blocked waiting on that printer to come back to you. Okay? Or a network device, right? Or an internet service. Okay? Or to some degree the memory itself in your computer. Okay? And do you understand the distinction between these two? Atomic and multi-part are not so they use single unit resource and multiple unit resource in Zybooks. Okay? This is, to my knowledge, not an official term. So as long as you understand the distinction, you can use whatever terminology you want. All right, so what does requesting a resource look like? When you request a resource, if it's currently free, the state of R is changed to allocated, and a pointer to R is inserted into the list of other resources of the process. In other words, you get the resource. If R is not free, then the calling process P is blocked. P's PCB is moved from the ready list to the waiting list of R, of that resource. Okay. Since it's now blocked, the scheduler has to be called to select another process to run. You must be the running process in order to ask for a resource. Okay? Only one process can be asking for resources at a time, and it has to be the one that's running. Okay? But if you want to release a resource, R's waiting list contains no processes. If that's the case, then the state of R is changed to free, and P continues executing. Now, I should mention, in both of these examples, both of these discussion points, this assumes that it's a single use or an atomic resource. This would look slightly different if it were a multi-part resource, right? The values associated with that multi-part resource would be updated. Okay? If the waiting list of R is not empty, then the process Q at the head of that Q list is allocated to R. The state of Q is changed to ready, and Q is moved from the waiting list to the ready list. That is how things get moved from a waiting list to the ready list. Somebody releases a resource. The act of releasing that resource calls the operating system to manage the list about that resource. It's become available. Is anyone waiting? Okay, yes. So they get access to that resource, and their PCB gets moved on to the ready list, right? They don't go directly to running. There is no link right here. This link does not exist, okay? Because just because you become unblocked doesn't mean you get to forego being scheduled again, okay? Does that make sense? All right. So what does the scheduler do? The scheduler determines which process should run next and starts the process. It's called after every create, destroy, request resource, and release resource. Okay? Every time that we create a process, destroy a process, request a resource, or release a resource, that's when the scheduler gets called. And then assuming that the ready list is implemented as a priority queue, then the scheduler finds the highest priority process on that list and performs a context switch. Incidentally, this is the context switch. Okay? Moving something that's still running off of the running queue into ready. Okay? And performs a context switch if that's the case. If either of the following conditions are met, the priority of the running process P is less than the priority of Q. Okay? P is the currently running process. Q is the highest priority process on the ready list. Or the state of the running process P is blocked. Okay? So the other aspect of the context switch would be this and then this. Okay? So this and this, or this and this is what the context switch is. Okay? Any questions? All right, let's talk about an entirely new thing. Well, it's not an entirely new thing. It's a further abstraction of a thing we already know about. Okay? We know about processes. Processes are the fundamental unit. Well, let's not call them that anymore. They are the first level unit of processing. Okay? Of running a program. All right, so then what the heck is a thread? Okay? Processes and threads have something in common. Okay? Processes, can you see this? Okay. Processes are a program in execution. Okay? Threads can be thought of as a sub-program or a partial program in execution. Okay? Here's the insight that comes out of threads. Programs can often be broken down into independent subparts, right? And I mean something very specific when I say independent. It means that whatever the one subpart does will not affect the operation of any of the other subparts. Okay? So calculating something, the other subpart doesn't need to know that before it can go. Accessing memory, the other subpart doesn't have any access to that memory. Okay? And so as processes, as programs get more complicated, it's sometimes possible to break them down into their component pieces. Okay? From the programmer's point of view, we often do this with like functions. Sometimes we use functions this way, right? So since this is true, it seems wasteful. It's a sad thing. It's sad that all independent subparts are simultaneously blocked when one of them is. Okay? That's true if we treat this all as a single process. Okay? And so threads are an attempt to answer that. Okay? Instead of having a single PCB for the process, okay, we can instead have control blocks that are TCBs. All right, so far we're in love with CBs. We've got process control blocks, we've got resource control blocks, and now we've got thread control blocks. Okay? Thread control blocks have things in common. Okay? All the threads of a process, okay, will all access, so the thread control block, and there are potentially multiples of them, will all access shared resources that include the instructions. Okay? The instructions, right? Potentially the memory. Okay? Potentially some other things, depending on your architecture. But at the very least, they all have access to the same instructions. Okay? Right? The other way to do that is to logically or physically break up the instructions themselves so that each of these threads has its own copy, and you can see how that would be a waste of space. Okay? When you run, you guys told me that you guys haven't had architecture. Haven't had an architecture class? Most of you haven't, or have some of you had architecture before? A couple of you have? Okay. So when you have your set of instructions, okay, that's stored in memory, here's my program, these are the instructions. Okay? One place in cache is called the program counter. And the program counter points to the next instruction to be executed. Okay? And so then you have what is it? The fetch execute loop. Yeah, what is it? Yeah, yeah. Fetch decode is what I was trying to think of. Thank you. Yeah. Fetch, execute, or decode, execute. Yeah. Okay. So this is the cycle that your processor runs through. Okay. Fetch means an instruction is a bunch of binary that when broken down, it has an opcode and a series of parameters. Okay. Fetch gets that, okay, and stores that instruction in a place in memory on the chip. Oh, I'm doing this off the cuff. What is that called? Anyway, the current instruction goes in that place in memory, okay, and will be executed. So fetch, decode, break it into its individual parts, execute, okay? And then the next thing that happens is the program counter gets updated to the next location, okay? And goes through that fetch, execute, fetch, decode, execute cycle. One of the things that can happen when you execute an instruction is that it can be a jump instruction, right? And so instead of updating the program counter to the next thing, the program counter can go anywhere, right? It can go way down here somewhere, okay? Or it could jump back up to the top and do the same instructions over again, right? Jumping back up would be like iterating. That's what happens when you have a loop. Jumping to another place in memory would be like calling a function, okay? And so the execute cycle updates that program counter, but by default, it just goes to the next line because by default, we execute sequentially, okay? Unless we do something with a different instruction that causes that non-sequential execution to become something else. Iteration, selection, function calls, okay? Generally, when we talk about processes, there's only one of those program counters. But when we talk about threads, each of these threads gets its own program counter, and that program counter can be pointing to different locations in the instructions. Okay? So each one of these threads gets its own, executes its own fetch, decode, execute cycle, independent of the other one, and independent of the fact that they're all part of the same program. They're all running off the same instruction set anyway. What happens when this guy executes his instructions does not affect what happens when this guy executes his instructions. They are independent components of the same program. And this is where the benefit comes in because there's a lot of overhead to doing this so far. This is where the benefit comes in. If we can get them scheduled independently, okay, then when one part of the program is blocked, it's possible that another part of the program could be running, okay? And so we get a higher percentage of from the program's perspective or the process's perspective, we get a higher percentage of the processor time, okay, because we have multiple threads. And from the processor's perspective, we get a higher percentage of use time because things that are being blocked are not making things that don't necessarily have to be blocked for the same reason wait. Okay? So it's a win-win from both sides. The operating system, it's a win-win from the processor side of the operating system and from the user world side of the operating system. It makes the programs It makes the programs execute more quickly, and it makes the processor more effective because there's less context switching between programs. Okay, does that make sense? Here's the relationship between the process control block and the thread control block. The CPU state is copied to every thread that belongs to this process. There is a program counter, okay, and SP. I don't know. What is SP? I forget. Program counter and what is it? Yeah, it might be a stack pointer. Anyway, your book says.
Yeah.
Okay.
Google says that one.
Okay. So your book says, because each one of these gets their own stack too, by the way, right? Because they might both be calling functions, right? And then thread state, right? So the process state is really becomes the thread state because the thread becomes the function of processing that the processor has to keep track of. And notice, these are the shared parts. They're shared between all the threads that belong to this process. Okay? All right, we're out of time, and I kind of thought we would be. So I didn't plan on talking about user space versus kernel space threads, but your book has a couple of sections on that, which you either have read or are expected to read before Friday at midnight. Okay? All right, so quick review. Haven't graded exercise 2 yet. Will do so. We'll have that done. My plan is by before end of day Friday, and also I'll have exercise 3 up before end of day Friday. Yeah, so be looking forward to that, and I'll see you guys next week.
Have you posted the meeting?
No, I have not yet. Well, the one for this week is 2/4 through 2/6. It's due Friday. That's been posted for a while. The one for next week hasn't been posted yet. Do you not see it on there?
It doesn't have a due date on it.
Yeah, it doesn't have any of that.
Oh, they should. I just looked